Hello, SpaceX. My name is Kim Wright, and today I'd like to tell you a little bit about one of my favorite research projects titled Investigating the Use of Wing Sweep for Pitch Control of a Small Unmanned Air Vehicle. This is my master's thesis in a nutshell. So you're probably wondering, why would you want to use wing sweep for pitch control? After all, elevators do a pretty good job. To make a long story short, I was interested in spot landing the way birds do. Of course, there are some neat small aircraft out there which can already spot land, but I had a new idea. Could I apply avian methods to a fixed-wing aircraft? I started out by looking at the way birds land. It quickly became evident that because they can move their wings in such complex ways, I would not be able to mimic this behavior in one shot. However, I did learn some things from observing them. One thing I noted was that the birds seemed to be using wing sweep variation for pitch control. I decided to focus on this small piece of the puzzle and got to work. Before I could create a computer model of an aircraft, I needed some geometry to start with. Luckily for me, my idea was inspired by birds, and therefore I had some great models to look at. It turned out that a barn owl worked really well. A few MATLAB scripts later, and I had defined my wing geometry. My next goal was to use CFD to predict pitch response to wing sweep, and to do that I needed to model changing wing geometry. I made another MATLAB script, this one relying heavily on a coordinate transformation matrix to generate new geometries based on wing sweep variation. This script created the input files for the CFD program, and many CFD runs later, the output supported my hypothesis. Wing sweep caused pitch response. Next, it was time to build the aircraft to see how well the concept worked in real life. The wing construction took the longest, and required the use of composite materials to achieve the unique, complex shape. The fuselage resembles a more traditional remote-controlled airplane with a twist. The nose houses an Arduino microcontroller system. The aircraft has the usual flight control surfaces, but also the unique rapid wing sweep function. Flight testing was exciting. The aircraft is hand-launched with a running start. At first, the pilot controlled the aircraft using the elevator for pitch control. The first time wing sweep was activated was using manual control. A knob on the pilot's transmitter directly commanded wing sweep angle. The first time this was tried, the response was obvious. The aircraft performed a loop. The pilot returned the wings to neutral and landed. Several flights were performed, and wing sweep continued to cause noticeable pitch response. The onboard data recorder was used to capture the aircraft's sweep position, pitch angle, and elevator position. Here you can see that when the wings were swept forward, the aircraft pitched up. Because the elevator was held neutral during this time period, it was concluded that wing sweep was causing the pitch response. After observing the pitch response due to manually controlling wing sweep position, the onboard microcontroller was used to close the loop. When the pilot was ready, he flipped a switch on the transmitter to signal the aircraft to take over pitch control, using only wing sweep for input. Unfortunately, a wind gust caught the aircraft on landing at the end of the flight test, causing it to crash. This brought an abrupt end to the flight test program. I picked up the pieces and collected the test data. The data was promising. The controller appeared to be settling at the desired pitch angle. This showed that the use of wing sweep for closed-loop pitch control was possible. With this knowledge, I defended my thesis and graduated. Not to worry, though. I couldn't leave my faithful airplane in pieces for too long. It was successfully repaired. I hope you enjoyed my thesis in a nutshell, and thank you for watching.